My name is Sungkyoon Kim, a professor of Department of Environmental Health Science at SNU. This is a lecture series of Introduction to Public Health and Graduate School of Public Health in SNU. I made this video clip for flipped learning. Students, you should watch this video for your study before the main lecture. I'm touching the key concepts and you need to explore more with this material, plus other resources. In the main classes on April 28th, we will have a Q&A session and quiz plus a discussion session. The title of this lecture is Living in the Chemical World and What We Should Do to Make a Better World. We will cover the need we need to tell the risk from harm. And the key concepts of the risk and biomonitoring. And also we will have a discussion. For the discussion, I will give you some considering issues. We are living in the chemical world. Everything we eat, drink, clothe, and use is they are associated with the chemicals. There is no exception. We are exposed to chemicals intentionally or non-intentionally. Actually, every single chemical is toxic. Long ago, Dr. Paracelsus said, all things are poisons, for there is nothing without poisonous qualities. It is only the dose which makes a thing poison. Each chemical in this slide has a LD50, the lethal dose, 50 percentile. The amounts of the LD50 is the amounts required to kill the 50% of the population. Even excessive salt can kill human. A more toxic substance act less dosage. There are many toxic effects other than death. Endocrine disrupting chemicals can act at molecular level after a while or long time later. We need to tell risk from harm, otherwise confusion or turmoil will follow. Harm is another expression of the results of the toxicity. Toxicity is a sort of the properties of the chemical, corrosive and carcinogenic and endocrine disrupting, etc. The risk is a function of exposure and toxicity. Even in highly toxic chemical, we are safe if they were away from it. Then we can call the risk is a zero. I'd like to say the risk is a realistic danger, indicating the present safety given it usage or exposure. We need to distinguish between toxicity and risk. Let's say there is a report on detection of harmful chemical in baby food, which may cause concern. Sometimes it grows into fear or turmoil. In many cases, we made a ridiculous judgment in the past. There is no way to solve the problem. And this is not a way to solve the problem. As I mentioned, risk is a likelihood. However, many ordinary people or mass media want to know whether it is acceptable or not. However, the risk has uncertainty, and it depends on the state of our knowledge. Risk assessment is made in this diagram. This area is about the toxicity, toxicological scientists or health scientists that drive the guidance or reference levels. Then we measure the actual amounts of the exposure and compare them with the reference. And if it is more than the reference, then it is risky. So exposure is very important in risk assessment or risk determination. How can we measure the exposure? We can measure the amounts of the chemical in exposure media, such as water, air, or food, or consumer products. We can measure the we can make measurement of the chemicals or chemical-related products in our body as well. And we can call them as exposure biomarker because they indicate the exposure events. Biomarker is an indicator in biospecimen, such as urine or blood. They indicate some events happen, such as the exposure. Blood lead or blood chlorinated by phenyl indicate exposure to them, as in the case of alcohol in breath, they indicate drinking. This diagram is called as a exposure disease continuum. Let's take an example of benzene. We can measure the benzene in the air for exposure assessment. Benzene is not generated in our body automatically. If we measure the benzene in urine, it proves benzene exposure happened. Part of benzene in the air get into our body. We call this portion is the internal dose. And part of the internal dose of benzene will make some effects in this series of the health effects. So this portion of dose is called a biologically effective dose. Benzene oxide, which is the first very reactive metabolite of benzene, can cause a addition of product with the DNA or hemoglobin, as sort of the blood protein. Urinary benzene and benzene oxide DNA adducts are used as the exposure biomarker. The cystochromatid exchange, low count of blood cell or leukemia are indicator of health outcome, which are called as effect biomarkers because they indicate health effect happen. Not all people follow these steps in the same way. Some people have more susceptibility due to the different genes. The genotype or phenotype of the genes which make this role in these steps could be used as an indicator of susceptibility. So they are called as a susceptibility biomarkers. Since this is a sort of the smoking gun of event, especially for the exposure biomarker, biomarkers are very useful. We can identify the regulatory priority of exposure to chemical in terms of the body burden. We can identify the at-risk population exposed to chemicals. We can evaluate the administrative activity by checking the trend of the biomarker of exposure. let's take an example. This plot is very famous. Long ago, lead was used as an anti-knocking agent in gasoline in US, but it contributed the blood lead. So US government removed the chemical from the gasoline. Then they found the policy was effective to reduce blood lead in the public. Can we measure the body burden of a chemical? Let's move this slide. Yeah. Can we measure the body burden of a chemical? The answer is yes and no, because it depends on the chemical properties. The persistent organic pollutant is more abundant in blood, and they remain for a long time. This is log-log scale, but it is not in urine. Rapidly excreted chemicals could be found in urine more. However, the sample collection time is very important to utilize the exposure biomarkers. There are limitations of the biomarkers exposure, so we need to be very careful in utilization of the biomarker for the risk assessment. It does not tell the history of exposure by the spot the results of the biomarkers. Biomarker is an aggregate of amount from all sources, so by measuring it, we cannot tell the source of it. By the concentration of the blood or urine, by the concentration in the blood or urine, we don't know the input amounts. In other words, it's a intake amount. So we need another information to use the biomarker efficiently in risk assessment. Let's come back to risk. As I said, risk is a, hold on, I will skip this slide. This is another example of the explanation. So let's come back to the concept of risk. Risk is a likelihood for science, but it is acceptable among the stakeholders in politics. And risk is a perceived danger in public. As I said, toxicity relevant reference or guidance value, they are necessary for risk assessment or risk determination. Usually, they came from animal data. Let's say we got a no adversely effective level, effects level. We call this a no AL. Since they came from the animal, we put the conservative safety factor and we divide them by the safety factor. Then, let's say another example. Let's say we have a 1 ppm for the reference value. What about 0.7 ppm? Is it safe? Or how about the 1.3 ppm? Is it dangerous? Threshold limit value, TLV, is a reference value recommended by the scientists. The government adopt them for regulations. Let's pick up another example with the benzene. After World War II, threshold limit value of benzene was 1 ppm. Now it was cutted. Now it is a 0.1 ppm. Can we say the people at 1946 was stronger against benzene toxicity than those in the present day? By 1,000-fold. For this long period, scientists collect data and they make these kinds of the plot. See, there's no association between the points around the exposure over TLV and the percent adversely affected. So we can say TLV is not that protective. As our knowledge grows, we change TLV. Also, zero TLV is not practical at all. Actually, the reference value or the guidance value are combination of the scientific knowledge and social levels or the status of the acceptance among stakeholders. Facts are the reference level are necessary for risk assessment. However, very small number of the chemicals have them. Reference level are not bright line between safety and non-safety. They are just social acceptance by support of the science. Now, let's return back to the title of this lecture, Living in the Chemical World, What We Should Do. Usually, we get the information from mass media. How much do you trust them? How much trust their messages? Please watch this video clip. A TV reporter presents that there was a poisonous trees around their elementary school. Then, well, after a while, you will have a thought, and they wrote down what you thought. Since you learn and consider something in this lecture, you would say something. We will have a discussion in the main class. Another considering issue is can you distinguish facts and fakes? What is the better way to tell facts from them? Also, are facts enough? How about the context? I believe this thinking could be helpful to make a better world, especially for the safe one from chemical risk. This is the end of this lecture. We will see next week at Zoom. Please prepare your thought, and we will see the next week. Thank you.